We're going to solve one more example on subscript summation notation. The second example, using subscript summation notation for vectors a, b, and c, prove the following vector identity. A vector cross product with b cross c is a dot c times b vector minus a dot b times c vector. Okay, so let's call b cross c the vector d, okay? So that d vector can be written in terms of its components as di ei hat, where this is obtained by Lebesgue symbol epsilon ijk bj ck ei hat. So the ith component of b cross c is epsilon ijk bj ck, and for vector d this is in I hat direction, so it's ei hat. Okay, so what is a cross b cross c? A cross b cross c is the vector a cross product with vector d. So a cross d, we can write this as epsilon klm al dm in ek hat direction. Okay, and this is epsilon klm al. What's the mth component of the vector d? Mth component, so this is the ith component. Now I'm going to write the mth component. Mth component is epsilon m n p bn cp, and this vector is in ek hat direction. So ith component was epsilon ijk bj ck. Mth component is epsilon mnp bn cp. Okay, now let's group these together. I have epsilon klm epsilon mnp al bn cp ek hat. That's this vector. And in order to be able to use the Lebesgue identity, I have to have both m's in the same location, right? So I'm going to move this m over here. So noting that I'm going from m and p to npm. So m and p, npm, that's positive direction. So I have to multiply it by +1. So this gives me epsilon klm, and epsilon m and p is equal to epsilon npm multiplied by al bn cp ek hat. Okay, now I'm ready to use the Lebesgue identity. Kronecker delta, firsts k and n. Kronecker delta, seconds l and p, minus Kronecker delta, inners n and l, Kronecker delta n l, and outers Kronecker delta kp. So these are the outers. So I have Kronecker delta kp multiplied with al bn cp ek hat. Okay, so let's work on this first term here. This says whenever you see n, equate it to k. So let's do that. We have bk. And whenever you see L equated to P, so AL will become AP. And then I have CP. And minus, whenever you see L equated to N, so this is AN, BN. Whenever you see P equated to K, so this is CK, EK hat. Okay, so now I realize that APCP is the dot product A dot C. So I have APCP, which is the dot product. BK, EK hat is the B vector, minus AN, BN is the dot product A with B, and CK, EK hat is the C vector. So in vector notation, I can write this as A dot C vector, B vector, minus A dot B scalar multiplied with C vector. So A dot C gives me a scalar multiplied with vector B, minus A dot B gives me a scalar multiplied with vector C, which is the identity that I'm trying to obtain. A dot C B minus A dot B C. Okay, so in this example, we have used the cross product representation using subscript summation notation. Two vectors B cross C cross together will give us vector D. This means the vector D can be written as epsilon ijk bj ck ei hat. Okay, so A cross D is epsilon klm al dm ek hat. Then I ask myself, what is dm? Well, di is epsilon ijk bj ck, so dm is epsilon mnp bn cp. So I put the epsilons together, then I change the position of m so that the m's positions are the same in the two Levi-Civita symbols, epsilon klm, epsilon npm, and here I noticed that going from m and p to npm is in the cyclic permutations, it corresponds to positive direction, so this is not going to introduce a minus sign. And then I use the Levi-Civita identity, firsts, seconds, minus inners, outers. And then I notice that n's will be made k in the first term, and l's will be made p. So this is APCP minus, and l's will be made n, so a and bn, and then p's will be made k, ck, ek hat. So that gives me A dot C vector B minus A dot B vector C. That's the answer I'm looking for.